Bergson and the holographic theory of mind. Topic today, the gravity of general relativity, which is to say, in this framework, mathematics is the physical. And also to say Newton would not be too impressed. So this is a subject that I was going to avoid, but that book there by Sean Carroll made me take a look at it. So here we go. The general theory of relativity, a rock of physics, an epitome of thought for Mr. Einstein, has the symbol of that epitome. From Bergson's perspective, what would it be? I think an exemplar of this, the current confusion of mathematical explanation for a physical explanation, which is why current physics cannot be the basis from which we start a theory of consciousness, because you can't start a theory of consciousness from an artificial theory that's purely mathematics. So this is Newton's law of gravity. The mass 1 times mass 2 attracting each other proportional to the distance squared, or r squared, between the two, with a nice gravitational constant there thrown in, g, proportionality constant. Of course, one always asks right away, why does a mass exert an attractive force as opposed to a charge, which exerts an attractive force, but that's a charge. We have some vaguer understanding of that, but why just a mass? How does a bowling ball attract a marble? Interesting question. But this is what Newton said then about the nature of gravity. Hypothesis non fingo, that is, I feign no hypotheses. That is, he has no idea what gravity actually is. He has a mathematical description of its effect, but he doesn't know what it is. Did anything actually change with Einstein? Would Newton look at general relativity and say the exact same thing? Hypothesis non fingo. This is going to be as brief an exposition of general relativity as possible. Carroll devoted this book to an explanation that is at least pretty understandable. We're going to do far less, enough to see my point. He starts with special relativity, and especially Minkowski's geometric representation of special relativity. Right there, we're already seeing the geometric representation. The axes of the guy in the rocket, T2 and X2 there, are scissoring in for the geometric transformation, and you end up with a contracted time unit and an expanded space unit, even for the diagram. This is important because, to quote Sean, Minkowski spacetime is flat, static, and infinite. Einstein worked for a decade to understand how the force of gravity could be incorporated into his theory. His eventual breakthrough was to realize that spacetime could be dynamic and curved, and the effects of curvature are what you experience as gravity. So, going on, he says, so special relativity is a theory of a fixed, flat spacetime without gravity. General relativity is the theory of a dynamical spacetime in which curvature gives rise to gravity. So it's how is flat Minkowski spacetime transformed into a curved spacetime, which also brings in, quote, explains gravity. The geometrization scheme of special relativity, that's what we need to look at. What are we geometrizing? Well, this, in the little box there, the observers who's moving the velocity v, that'd be our guy in the rocket there, new time and space units, x prime and t prime. And there you see the Lorentz transformations with those two dimensions, x prime, the direction in which the guy in the rocket is moving. That's his new space-time, new length coordinate, shall we say, or length, x prime length, and t prime is new time. The y and z dimensions are unchanged. So if we take a 2D space-time, a time coordinate and a space coordinate, t and x And we imagine two events, E1 and E2. And then there's something called, as Sean calls it, and other people call it, tau, the proper time, what a clock would look like between two events. So there's the tau stretching between two events. And we could throw this whole thing into the Pythagorean framework where tau squared is equal to the change in the t dimension plus the change in the x dimension. So you have tau squared equals dt squared plus delta x squared after the a squared plus b squared thing of the Pythagorean theorem. And then with Minkowski, then we have the tau squared as if you notice the minus sign, delta t squared minus delta x squared. And so with moving at velocity v, as a rocket guy is, v, simply the change of distance over the change of time, delta x over delta t, or rearranging a bit, delta x equals velocity times delta t. Again, simply taking the what would v delta t equals, and therefore the tau squared at proper time is that expression there, delta tau squared, delta t squared minus v squared, delta t squared. Or a little more rearranging, and we get that tau equals, or proper time equals, the square root of 1 minus v squared times delta t. Ignoring something here that implicit always in this little mathematics here, as Sean Carroll lays it out, we're always dividing by c, as you see in the equations in the middle box there. But since c equals 1, doesn't mean a lot. We see is set to 1. So the proper time tau is shorter by a factor of square root of 1 minus v squared. So continue the geometrization. We can take that coordinate system we just saw and rotate it by an angle theta, as such. The angle theta now corresponds to the difference in velocity between the moving system and the at rest system. But in the Minkowski framework, with that minus sign for time, the coordinates of the moving system scissor in. Hence, just as in the last slide picture where we saw this, we're scissoring in. And so that's in the geometric representation, as we saw, you're getting that contracted time unit and expanded space unit represented in the geometry. So this is enough here for Minkowski's geometrization of special relativity, but this is the framework from which Einstein started to think about the general relativity. Minkowski's framework is the breeding ground for an endemic problem with all special relativity and GR theorists. It totally obscures the reciprocity of the two reference systems, or the two observers. This is Carroll's explanation of the twin paradox. So we have Alice on the Earth, just running along in the t dimension, just aging on the Earth, and Bob in the rocket. And Bob, of course, ages less according to the value for his proper time by a factor of the square root of 1 minus v squared and the change of time. So Carroll says what the twins find out at their reunion is that Bob has experienced less proper time than Alice has. At 99% of the speed of light, for every 1 year of time he has experienced, Alice will have experienced 7 years. End of proof for Carroll that special relativity explains a real ontological effect. Gray hair and wrinkles for poor Alice versus Bob's youth, a definite physical effect that isn't going to go easily away with reciprocity. To Carroll, reciprocity, however, means nothing. The word does not appear in the book. But, voila, this is the second Minkowski diagram that's required to represent the reciprocity of observers, an inherent, intrinsic absolutely necessary to special relativity. So now we have Bob, who's stationary, the rocket simply neutralizing the motion of the Earth, with Alice moving away and then back again. And so, of course, Alice now has a shorter properton by the same factor, 1 square root of 1 minus v squared delta t. Both Bergson in Duration and Simultaneity in 1923 and A.P. French, the MIT physicist, in his book Special Relativity in 1968, noted this 2 diagrams are needed to represent this, to represent special relativity properly. This is why special relativity can only explain these effects as though they're measurement effects, and why Langevin ruined the logical consistency of special relativity. Remember, a measurement effect. It's like using 2 different rulers. One's 6 inches long, one's 9 inches long. And so the toaster expands or contracts depending on the ruler being used. In special relativity, the rulers are light waves and synchronized or not synchronized clocks. Not synchronized if from a stationary observer's point of view, you're in motion and then your clocks aren't synchronized. Hence all the effects begin, but they're only measurement effects like the rulers in the toaster. Special relativity can't explain the actual real aging or between Bob and Alice. Alice now has tons of wrinkles and gray hair. Some other theory is needed. One meets this ignoring of reciprocity over and over in Carroll. He acknowledges the concept, this quote, the basic meaning of relativity in this context is that there is no objective preferred reference frame in the universe. We can only measure the velocity of an object relative to the motion of other objects, not in any absolute sense. For me then, in other words, Alice can declare herself at rest, Bob is in motion, just as we saw, or Bob can declare himself at rest, Alice in motion, as in the second diagram, and no one can say who is right. That's reciprocity. But this concept is simply disconnected in Carroll's mind from this one-sided, half-relativistic conception, where we have one Minkowski diagram and we only care that one observer is moving and the other is not. But this half relativity is the entire basis of general relativity. So general relativity is just, as I just noted, is built upon this half relativistic, as Bergson termed it, framework. Carroll, at points, will talk as though general relativity is truly, actually relativistic. But at these points, things become pretty incoherent. Another curious statement before we continue. So he notes, for any path, to calculate the total amount of proper time elapsed, we just integrate. And the integration, the delta t is the integration of little dt. So in other words, we're just taking that curved path, which means we're accelerating and taking little segments of it and adding up the segments into a big chunk, that integral of d tau. And we get the total change in proper time. So he says, sometimes people will suggest that special relativity works only for unaccelerated trajectories, and you need general relativity to handle acceleration. Rubbish. General relativity becomes important when spacetime is curved and we have gravity, as long as spacetime is flat, which is Minkowski spacetime. Special relativity applies, and you can consider any path you like. So again, reciprocity is so meaningless to him, he's forgotten why special relativity was limited to uniform velocity in the first place. Yeah, if you're plastered against the seat of my 1968 Camaro with 450 horsepower, it was souped up. Leaving the stoplight, you know you're accelerating. That is, you are definitely in motion. In other words, we can definitely distinguish which system is in motion and which is at rest if one is accelerating. But special relativity was limited to uniform velocity where we're not accelerating, precisely because then you have reciprocity. You can't tell who's moving. But he says later on in the book, you can tell if you're accelerating. So, in other words, it's incoherent. In actuality, Carroll has actually slipped into admitting the validity of Bergson's argument, namely that acceleration cannot have the special status of an absolute force that Einstein assigns it in the general theory. Velocity is the first derivative, acceleration merely the second derivative of change of position, and it's the rate of change of the rate of change of position. That is, both are relative. You cannot, both motions, velocity, a velocity, uniform velocity motion, and a accelerated motion are relative. So, as he noted, we can derive the Lorentz equations in the context of acceleration. If you can't, calculus is useless. And of course, this has been derived. It's no problem. With these generalized equations, nothing changes in special relativity, acceleration. So all those arguments that, oh yes, you have to have acceleration, that explains it, falls away. They fall. That is acceleration explains the real effects just simply collapse because you simply generalize special relativity to acceleration. In that case, then, noting that, of course, you're ignoring that you could tell the difference between the two, because if you're in the Camaro, like I said, you know you're accelerating. But Carroll is oblivious to the bad implications for general relativity. Again, you could ask, well, why are you plastered against the seat? Then, if acceleration doesn't have this force effect, as Einstein's assigning to it, and one might wonder if actually the reference system, namely the car, with the seats, the bolts, the wheels, and the person in the seat, is really breaking up then into multiple systems that it actually is. That's what Bergson's argument, duration, and simultaneity. It's actually multiple reference systems, and they're all on the acceleration just breaking up, and that's what you're feeling. This takes us into interesting questions that I'm not going to go into. So back to curving Minkowski. When Minkowski suggested in 1907 that the best way to think about special relativity was in terms of a unified four-dimensional space-time, unified in terms of electromagnetism as well as general motion, Einstein was skeptical. But Einstein grew to appreciate the space-time formalism, especially as he turned his attention to the question of how to incorporate gravitation into relativity. He ultimately became convinced that gravity could be understood as a manifestation of the curvature of space-time itself. But how to turn this insight then into equations? Well, this leads to a whole list of subjects. First of all, you're talking Riemann. Riemann's task from Gauss to examine the foundations of geometry, which brought him to looking at spaces, describing manifolds, expressing curvature of spaces via tensors, then tensor notation, the metric tensor, Riemann's tensor for curvature, the Ricci tensor, which is a reduced index form of Riemann's, the energy momentum tensor, and I noticed what's a tensor here. Here you've got a little matrix there, the G of ij, G1, G2, G3, etc. And where you have each entry, G of ij, G11, etc., G12, holds a function. So there's actually functions in each of those elements describing the curvature and length of a line element in space. Now, you kind of get a picture on the right side of a little bit the notion of a line element, but you'd need, for the length of a line element, to understand it a little better, I'd have to throw that into polar coordinates, but that can be done. So you're looking at line elements, length of line elements in space, describing that. So at G12, for example, there's a function multiplying the displacements dx1, dx2 in the line element. So this tensor can describe the curvature of an entire 3D space. And then you got Einstein's task, expressing Ricci as a scaling factor of the energy momentum tensor, such that the law of gravity is captured in the manifold. And Carroll spends at least 50 pages on this. This is Einstein's root, ultimately, to this equation on the right here. Notice the 8 pi g times the energy momentum tensor. 8 pi g is what's getting us back to Newton's law and the gravitational constant. I'm skipping describing this root. We're going right to an equally valid equivalent root. For in this root, the answer to what would Newton say is stark, simple, and clear. So in number 72, we went through the Lagrangian and the principle of least action. I got some pictures here. So of things in that discussion. For a particle in motion, the Lagrangian L is the kinetic energy minus the potential energy, or L equals T minus V, or the kinetic energy minus the potential energy. So in the little picture I have on the right there of this pendulum swinging back and forth, what you have is the constant transformation of potential energy into kinetic energy. You've got max potential energy, and as we move down, we're getting the minimum potential energy at the bottom of the curve there, but you've got max kinetic energy, etc. So potential energy is decreasing energy, kinetic energy is decreasing as you go back up. So ultimately, what we're showing with this Lagrangian, when you again, the picture with the garbage can there, throw that garbage can in a gravitational field, and it describes that path. And that's the least action path. That path minimizes the difference between the potential energy and the kinetic energy. It always keeps it minimal. So least action. And that's considered the explanation for that path. Remember Sabina's critique about all this. You've got that integral from TA to TB there, up in the top just above the garbage can. Or down below my picture there, the action. But that is, you have an integral then from the present TA into the future TB. So the mathematical quote explanation unquote implies that the object knows the future, that the garbage can has read the book on making Lagrangians and affecting the least action path. It's sort of problematic. Again, my little picture there, the TB, the future point. So general relativity is a field theory. You've got the metric tensor, G mu there, is a field that has a value at each point of space-time. So it's not just about a particle moving somewhere, as we started out with the Lagrangian discussion. In a field theory, the Lagrangian is defined by constructing a function, the Lagrange density, we'll call it L for ease, and then integrating over all of space as such, where d3x there is the three-dimensional space. And then the action S is the integral L over space-time. So there we have it. Now to get Einstein's equation, we need to guess the appropriate Lagrange density. To quote Carroll, there's only one possibility, the Ricci curvature scalar R. We could also include a Lagrange density for matter. It will depend on what type of matter we're interested in, and we need Newton's constant G in there somewhere to get the strength of gravity to work out correctly. The final answer turns out to be this equation. That's the least action description of general relativity. Note the 16 pi g in there. So what has happened here? Remember, Euler-Lagrange already expresses the path of objects per Newton's law. Okay, so if we start with the green box there for that motion, dropping the garbage can through a gravitational field, we have the equation my double dot equals minus mg. Okay, so we take the Lagrangian, and then the Lagrangian L, they're defined as the minimizing of the potential energy, kinetic energy. Stick that in the Euler-Lagrange equation right there, and solve a bunch of differentiation rules. We end up with the green box below, exactly what we started with. In other words, the Lagrangian defines, and the least action defines is simply defining equivalent to Newton's original law. So remember, the Lagrange already expresses the path of objects per Newton's law. So we express space abstractly as a curved manifold, including the Lagrangian and the tensor expression thereof, and simply made sure post hoc that the curving of the structure reflects the force of gravity g. You got to think about that for a second. We simply backed into making sure the curvature, the geometrization, reflects the force of gravity g. Einstein did the same, just a different route. So there we have, again, the 8 pi gt. The way we've written down Einstein's equation doesn't include some undeterminate constant of proportionality, but rather the specific factor 8 pi g, where g is the same constant that appears in Newton's law of gravitation. You can't derive this by pure thought. What Einstein did was to consider the weak field limit, in which gravity is weak and space-time is almost flat, but not quite. In those circumstances, we know that a good theory of gravity had better reproduce Newton's inverse square law. In order to make that work out, the constant in Einstein's equation must be 8 pi g. So what would Newton say? Well, I think this. You've nicely expressed the paths of Euler-Lagrange and a curved geometrical structure via your geometrization of things. But you've simply brought in the constant of attractive force, g, post hoc. Yes, curiously, this is a bit better for explaining Mercury's perihelion, that is, the perturbations or changes in Mercury's orbit. And I think we can throw in the prediction and existence of black holes, I think. But still, I see nothing has really changed since I left this planet, other than studying the same laws, now within a geometrical structure. Yes, I even grant that the inverse square relation drops out as an intrinsic feature of this geometrization. Stop for one moment, comment on that. I saw very recently a short YouTube featuring Edward Witten, a very heavy quantum gravity theorist, whom I also saw Eric Weinstein, a heavy theoretical mathematical physicist, saying everyone's afraid of. Witten said that the inverse square law fell naturally, had to be a part of the structure of Einstein's general relativity theory. It's his mathematical structure. It fell out naturally, intrinsically. Yet when you look at Carroll's description of the origin of it, he says, well, this really came via Schwarzschild, who was looking for the equivalent of the inverse square law. Now that's already a red flag, looking for the equivalent of the inverse square law and finding a solution to Einstein's equation for the metric in the empty space around the isolated spherical bodies such as the sun. Meaning, basically, Schwarzschild began visualizing taking a large gravitational body such as the sun and kind of backing into how that would bend space-time, and then how it would do so equivalently to the inverse square law. Hard to avoid an ad hoc interpretation of this. Another way to put it is, what if the inverse square law didn't exist? If Schwarzschild didn't know about it? Was there then some other solution that worked with Einstein's equation that worked just fine, except it didn't express the inverse square law? Interesting question. I'll grant what Witten says in Newton's statement here. I'll grant it that it's an intrinsic feature. Yet, I think I've made the case clear that, well, I don't quite trust the physicist in a whole lot of things and I just don't accept their statements at face value anymore. But we'll accept it. But I don't think that changes the issue at all. To go on with Newton's statement then. But as far as actually understanding what gravity is, I would still have to say hypotheses non fingo. That is, I still don't have a clue what gravity is. So Carroll's non-concept of reciprocity emerges here and there. One example. He describes how per general relativity, as you travel from the Earth to the Sun, your proper time would slow. And then he shows that equation there. Note the G in there. So the proper time d tau squared is changing as a function of the gravity and the distance, etc. Radius of radial mass from the r is the distance in the radial coordinates from the mass m. You rendezvous back with your friend at some time, at some value of coordinate time, but your elapsed proper time will be less than that. You've aged less, measuring less time on your clock. It's much like the twin in Minkowski space who zipped out near the speed of light. And then he says, this is a vivid illustration of what the idea that gravity really is geometry. In other words, a mathematical explanation is a physical explanation. Or as a Zen koan, mathematics is the physical. There's no possibility of reciprocity here. If you've gone out to the sun, hung around next to it, and your clock is slowed, your earthbound friend cannot possibly say, but reciprocity. You were stationary, I was moving. The slowing of your sun-slowed clock cannot be made to go away by invoking reciprocity. Not that Carroll's wrong in this respect. There is not a trace of reciprocity in general relativity, but acting like general relativity is a generalization of special relativity is absurd. Somewhere in the book, Canales relates a conversation with Einstein. His conversant had stated something to the effect that obviously Bergson did not understand special relativity. Einstein instantly corrected him. Oh no, he understands it perfectly. The implications of this are a bit shocking. In my opinion, Einstein knew well that Bergson was correct. Langevin had destroyed reciprocity and special relativity, and thus the logically consistent structure of SR, which only, in other words, the logical consistent structure, the reciprocal structure, can only explain measurement effects, can only explain effects as measurement effects, not as real ontological effects, like clock slowing, muons living longer, twins differential aging. But if they really are slowing, the twins really are aging differently, it can't explain them. But by the time of his 1922 debate with Bergson, he had already authored the magnificent general theory, where reciprocity cannot be found. Thus, he was willing to live with the illusion, in my opinion, that it is now the current, ubiquitous, non-reciprocal, generalized by general relativity, explainer of ontological effects version of SR. He was just willing to live with that illusion. That's what I think happened. So next we'll see. Till then, signing off.